The theme of this video is to determine reaction orders from rate concentration plots. So last time we introduced this idea of a rate concentration plot, imagining a simple reaction here, just one reactant forming one product. And the rate equation for that is the rate constant multiplied by the concentration of the reactant raised to a power r, which is the order. And the basic idea in the last video was that if we can plot a graph which shows the reactant concentration on the horizontal axis and the rate on the vertical axis, then we can determine by the shape of that graph what this order actually is. So let's have a think about what those possible orders are. So we're going to go for r equals 0, which is what we call a zeroth order reaction. Now if that's the case, then effectively, if we just drew up a little table of values here for concentration of R and the rate, then let's say R is 1, then because it's 1 to the power 0, well, that's just going to be 0. So the rate is just going to be 1 to the power 0 is 1, and therefore the rate is just going to be K times 1, which is just K. Let's increase the concentration. 2 to the power 0 is still just 1, and so K times 1 is K. And it doesn't matter what concentration we decide. We could use a concentration of 1,000. We're still going to get a rate of K. So it doesn't matter what the concentration is, the rate remains constant, and so we're going to have a line that looks like that. That's supposed to be a horizontal straight line. So this here is R equals 0, a zeroth order reaction. Now let's try another option, which is R equals 1. This is what we call first order. In this case here, it's a directly proportional relationship, so I'll just write it out there. Rate equals K times R. So in this case, if we were to draw up a little table of values again, then the rate concentration here, rate there, concentration of 0, we'll just start off with, well, K times 0 just makes 0, K times 1 makes K, 2, 2K, 3, 3K, and so forth. So we've got a simple direct proportional relationship where we're going up for every increase of 1 in concentration, we go up by K in rate. So that's going to look something like that. So that's going to be R equals 1 in this case. Now, next type of reaction that we consider at A level is what happens if R equals 2. So we have what's called a second order reaction. And if that's the case, then we've essentially got rate equals K times concentration of R squared. And so we're going to get a graph that looks like R squared. So let's just do a table of values just to check. So we use our same concentrations we've used here, 1, 2, and 3. And this is the concentration of reactant, the rate. So when concentration of reactant is 0, this is going to be K times 0 squared. Well, 0 squared is still 0, so it's going to be 0. When the concentration of reactant is 1, 1 squared is 1, times K is just K. 2 squared multiplied by K is just going to be 4K, and 3 squared multiplied by K is just going to be 9K. And so if we think about what this is going to look like, then imagine we have a concentration of reactant ranging here up to about, well, let's see, so yep, this is going to go up to 3 there. So we're going to have a curved graph here. So it's going to start off being a little bit slower, and then it's going to go up like that. So this point here might have been when the reactant concentration was 1, in which case these are equal, but this is rapidly going to overtake. So this is R equals 2. So that's the different shapes of the rate concentration plot depending on the orders of the reaction. So a zeroth order reaction just gives a flat line, first order reaction gives directly proportional diagonal line, and R equals 2 gives a quadratic graph, which is going to be much, much faster as the rate as the concentration increases, the rate increases much more steeply.